Okay, so now let's talk about the comparison between an addition reaction and an elimination reaction, because these are kind of the inverse of one another. So this is an addition reaction, is starting with an alkene, and then you have the addition of these two groups, in this case, X and Y, and they're going to be placed on either one of those vinyl carbons. Right, so that's an addition reaction. You're adding something to this double bond, breaking this pi bond here and replacing it with two new substituents on either one of those carbons. In this case, this was X and Y. Okay, and so that would be the inverse of an elimination reaction. Right, an elimination reaction would be going the opposite direction. There are many different addition reactions we're going to talk about. All of these, this is sort of like your master cheat sheet table here. We're going to review each one of these reactions individually, talk about its various features, all that sort of good stuff. But you can see they all follow this same pattern. They are all addition reactions. You're breaking the double bond, and those vinyl carbons, or what used to be vinyl carbons, are each getting new groups on them. When we, in our addition reactions, what we're going to do is we're going to see our double bond playing the role of or the pi bond playing the role of the electron pair donor, also referred to as the nucleophile, right? So this can either be as a base, it's an electron pair donor as a base, which really just means that the electrophile is a proton, okay? Or the electrophile can be an electrophile that's not a proton, in which case we would call it sort of a nucleophilic attack. But in both of these cases, what you have is the pi bond in our alkene is going to be an electron pair donor. So it's either going to be playing the role of a base or a nucleophile in all of these reactions. And again, these are sort of inverse of one another, our addition and our elimination. So elimination reactions were a big topic of last class. Right, so if I had replaced this, for example, with a bromine, we would have talked about the different conditions in which we could have an elimination reaction occur. So these two, addition and elimination, are inverses of one another. So let's look at them with regard to our free energy term here, right? We know that if we're going to predict which one of these reactions occur under certain conditions, well, that means that delta G has to be negative. Okay. So first, let's take a look at that delta H term. Remember, we talked about how you can predict delta H based on bond association energies, right? So calculating how much energy you have to put in to break bonds and how much energy is going to be released when new bonds are formed. Okay, so this would be looking at the addition reaction. We see that the addition reactions are enthalpically favored, right? Because if we calculate all the bonds being broken versus all the bonds being formed, we see that actually energy is being released in these addition reactions. The bonds that are being formed are stronger than the bonds being broken. Okay, and that has a lot to do with the fact that sigma bonds are stronger or more stable than pi bonds. When we talk about the, again, this is now looking at the addition, these reactions are not entropically favorable, right? So they are not favored in terms of entropy, and that's because we're starting out with two reactants and we're only going to one product. So we lose that translational freedom that we would get by having those two separate molecules, right? They can randomly move around independently. Once you lock them together, they've lost that translational freedom. So there's this push-pull going on between the entropy term and the enthalpy term in these types of reactions. Addition would not be entropically favored, which means that elimination is more entropically favorable. So we see we have this push-pull, right? So delta G. Well, if we are at low temperatures, such that that enthalpy term is not as significant, right? Low temperatures means that that term's not very significant. Then our delta H term is dominant. And so at low temperatures, we would favor the addition product. If we go to high temperatures, that means that this term right here is that much more important. And so at high temperatures, we would favor the elimination reaction. Okay, so these are inverse of one another, but we will make sure when we're talking about addition reactions that our temperatures are on the lower end compared to what they would be for elimination reactions.